Behavior of simple enzymes or reaction kinetics of simple enzymes is explained by Michaelis Menten equation. Michaelis Menten equation is shown here. So initial rate equals maximum reaction rate multiplied by concentration of substrate divided by concentration of substrate plus Km, which is Michaelis constant. What is Michaelis constant and derivation of this equation is explained in the previous presentation. So at low concentration of substrate, substrate concentration is considerably lower compared to Km, to Michaelis constant. And then reaction is the first order with respect to substrate. Simply we can ignore concentration of substrate or factors, concentration of substrate plus Km. Concentration of substrate number is so small that within our margin of error we can replace that with value for Km. At high substrate concentrations, then concentration of substrate is considerably higher compared to Km, and then reaction is zero order. Now, it is very important for us to be able to determine Km, Michaelis constant, and Vmax. Since Vmax is approached asymptotically, it's not possible to obtain accurate value from simple graph. So we cannot attempt from a graph to figure out either value for Km or Vmax. But solution is to transform Michaelis Menten equation into a double reciprocal plot, basically to linearize the graph. So we simply perform mathematical operations. There are a number of different mathematical operations where we can convert a graph that contains a curve that is nonlinear to something that is linear. In this case, a double reciprocal plot is the operation that we do. So we take reciprocal value of each side of the equation, and so this is double reciprocal plot. And you can see that it corresponds to general equation for a straight line. So we have basically made this dependence linear. So general equation for a straight line is y equals ax plus b. A is the slope, and then minus b over a is the x-axis intercept, and b is the y-axis intercept. Here is what the actual graph looks like as a double reciprocal plot of Michaelis Menten equation, and in this case slope a is Km over Vmax. X-axis intercept is minus 1 over Km, and y-axis intercept is 1 over Vmax. So as you can see from this plot, from double reciprocal plot, we can obtain accurate values for Km and Vmax. Now, Michaelis constant, or Km, is a measure of the concentration of substrate S required for significant catalysis to take place. And it also depends on the pH of the medium. It depends on the temperature, and it depends on the ionic strength. Now, for many enzymes, Km provides very good approximation of the concentration of substrate in vivo, which means that enzymes have evolved in such a way that they have significant activity at substrate concentrations that are commonly available, that are typically present in a cell, for example. Km is also a measure of the strength of the enzyme-substrate complex. So Km is actually a combination of individual rate constants for individual steps of the enzyme catalyzed reaction. And those individual steps are given here. So first step, enzyme plus substrate to form enzyme-substrate complex, is usually the fast step. Forward step would be K1 constant, and reverse step K minus 1. And then second step, conversion of enzyme-substrate complex into enzyme. plus product has rate constant of K2. If reverse reaction, K minus 1, is much faster than K2 because this is the fast step, then we have Michaelis constant that basically corresponds to K minus 1 over K1. And that means that really reaction rate depends only on the rate determining step, formation of enzyme substrate complex, and that is and Km then tells us how strong this enzyme substrate complex is. So high value for Km indicates that there is weak binding, and low value for Km indicates strong binding. So high value for Km means that enzyme substrate complex is very weak and reverse reaction is rather fast and rather easily occurs, while low value for Km indicates that bond between enzyme and substrate is rather strong and reverse reaction is not that significant. But this is valid only, remember, it's mentioned already at the beginning of the slide, when K minus 1 is much larger than K2. Vmax is related to the turnover number of the enzyme. Actually, turnover number is general concept in catalysis. It doesn't apply only to enzymes, but to all the catalysts. Any catalyst in chemistry, inorganic catalyst, organic catalyst, we can always define a turnover number. And turnover number is the number of substrate molecules that an enzyme converts into the product per unit time, when the enzyme is fully saturated with substrate. Typically, we express turnover number per second. So how many molecules of substrate, enzyme, or in general catalyst processes per second? It could be also per minute or some other unit of time. Of course, the higher the turnover number, the faster the reaction. That means the more efficient the enzyme is. And Vmax, the maximal rate of the reaction, basically reveals the turnover number of the enzyme. So the turnover number is equal to K2. And so for that reason, we sometimes call K2 also K cut. So that's the same concept. Now, one important quantity is ratio of K cut over Km, or K2 over Michaelis Menten constant. So when concentration of a substrate is much larger than Km, then rate of reaction equals maximum reaction rate. So under physiological conditions, concentration of substrate over Km is typically in the range of between 0.01 to 1. So ratio of the two, concentration of substrate over Km, is in that range. And so the rate is typically between 10 and 50% of Vmax. Now, if we consider that initial rate equals K2 multiplied by concentration of enzyme substrate complex, and concentration of enzyme substrate complex equals concentration of enzyme multiplied by concentration of substrate over Km, then we can derive this equation for initial rate. And so if concentration of substrate is much lower than Km, then concentration of enzyme, free enzyme, is basically equals to total concentration of enzyme. Very small amount of enzyme is bound to substrate. And then we can write expression for V0 as K cut over Km multiplied by concentration of enzyme multiplied by the total concentration of substrate. Simply, it's very difficult to figure out concentration of enzyme substrate complex. But we know the total concentration of enzyme and the total concentration of substrate because those are, we can obtain those before the reaction. We can determine those before the reaction. Now, K cut over Km ratio is the rate constant for the interaction of substrate and enzyme. And so that value, K cut over Km, is a measure of catalytic efficiency. What that means is that K cut tells us the rate of catalysis, how fast the reaction is, and Km, the strength of the enzyme-substrate interaction. It's different for different substrates, and the higher the K cut Km ratio, the higher the preference of the enzyme for particular substrate. So that means the more specific the enzyme is. So if K cut over Km value for particular substrate is very high, that means that enzyme is highly specific for that substrate. On the other hand, non-specific enzymes will have relatively low K cut over Km value. So that completes this brief discussion of Michaelis Menten equation.